Everyone to another NGS seminar. And today we have Ana Maria Elek with us to talk about R, functions, and fundamentals. Ana Maria is one of us, an active member of the NGS Society, and she is currently a PhD student in systems biology at the Center for Genomic Regulation in Barcelona, Spain. Her work currently is to answer the many open questions in the evolution of gene regulatory mechanisms, specifically those driving diversification of animal cell types, primarily by integrating single-cell transcriptomics and chromatin accessibility data. She graduated from the University of Zagreb, Croatia, and for her master's thesis project, she developed an R bioconductor package for the analysis of codon usage. So we're happy to have her today to learn more from her experiences using R. As usual, everyone, please send us your questions during the seminar in the chat section, and for Ana Maria, the floor is yours.
Thank you for this introduction. I'm really happy and excited to be from speaker that helps the various helps and I'm also already talking about which I really like. I think it's a great tool for great biologists and so this webinar is aimed at people who know something about
Ana Maria?
and follow the
Ana Maria, you have a terrible echo. We cannot understand you.
Hello. Sorry. I can't hear you. I can't hear you. Maybe
Maybe we will check it.
Can you just mute yourself? Yes. Okay. I hope there will be no technical issues or something. I will try to speak louder and clear and slower than I usually do. Let me just give a second. Yes. I had. So Gladys is saying I also had problems with her microphone, but let's hope it's not happening for everyone as well. So the aim of this webinar is to introduce you to some underlying logics of R and to so that you can understand how things that you code in R actually work, how are they executed. And by knowing this, if you understand this, you will then be able to modify your code and write your code in a way that will run faster and be more computationally efficient. So like I was saying, if you followed our first two seminars on R, you should have no problem in following this one. There will be nothing super advanced, but I hope you will learn something. So in terms of material that you need, I shared the link to GitHub repository where you can download the R Markdown notebook, which if you also followed our previous seminar, you should by now be familiar with how this looks. If you don't have R installed or you don't want to use your local installation, you can follow the link to RStudio Cloud project, which I have open on my screen and which you can see, and you can follow and run the code there. Or alternatively, you can just look at the compiled HTML version of the notebook that I also upload in the repository, and just you don't need to run. There's not going to be a lot of things that you will not be able to follow if you don't execute the code yourself. So I say let's start it. Let's get started. First thing that I have here in the notebook is the setup, and if you're running it, make sure that you have just these couple of packages installed so that you can run the examples in the notebook. This code in this chunk will do it, and then just load them in the next chunk, and we can go on. So the first thing that I want to talk about is something called variable binding, and this means So if you follow the introduction and if you know some basic part, you know what kind of data types and we have in R, and you know how we can create different variables. But what you probably don't know is how is this functioning under the hood. So what happens, for example, when you execute the code in our first example, where we create integer vector of 3 elements, like 1, 2, 3, and we assign it to variable called v1. It's easy to do it, and I will be running the examples line by line usually. And okay, sorry, I did a mistake. I didn't load the packages, which I was telling you to do. Anyway, so we create our first vector, and now this is available in our environment. This vector, you can, if you're using RStudio or RStudio Server, you can see it on the right side. Now in the global environment, you have now the value v1 associated with numeric vector that we just created. We can also find the exact memory location of this vector that we created using this package Lobster. In this package, there are like many very useful functions for exploring under the hood where the objects in memory are and so on. And we will first use this one called object like object address. And then we can see for our vector that we have some very long string, which is actually location in memory where our string is stored. Let's now say, for example, that we want to change our vector. If we want to, in the next, like the first element in the vector, we want to change it to p0. What actually happens? You would expect that we just still have the same vector, but it has just a different first element. But if you look at the address of this vector now, you can see that it's changed. So this identifier is no longer the same. And this is one of the characteristic behaviors of R, something that happens often, is that when you modify an object, what R does is actually it creates a copy of the object and stores it somewhere else in the memory. So why is this happening? So this is because when we created the v1 vector, we wrote the arrow pointing from the vector to the variable name. But what actually happens under the hood in R is this: actually the variable name gets assigned to the object. This is like very important to understand, because if you know this, it helps you to understand how R works and how to avoid making copies. So the object or value in R does not have a name. It's actually the name that has some kind of value or some kind of object associated to it. It's a very subtle difference, but it has quite important applications. So instead of having just one vector, we had two different vectors in memory, which is not a problem for vectors, but can become a problem when you're working with objects. For example, let's look at the lists. This is the same behavior happening with lists. So if we create similar thing like before, but instead of vector, we are creating a list. And then let's say we want to create a modified list, in which again we will replace the first element which used to be 1. Now we're going to replace it with 2. And if we look at the addresses of these two lists that we created, there is another function in the Lobster package which lets you inspect these addresses. You see that the output is longer, so for you can see the address for each list and for each element in the list. So the first line is the list, and this is the second list. So they are different, of course, but then you have the elements. In the first list, the first element and the second element and the third element. Each element of the list also has its own address, which was not the case with vectors. But when you look at the second list, which we modified, you can see that the first element, which we changed, now has a different address when you compare it to this one. But the second and the third element, they have the same addresses. So they are not really copied. So how is this happening when we just said that whatever you modify in R, it creates actually another copy of the object? Well, that's the thing with the lists, that the elements of the list are actually not objects. They are just pointers to the object. just like variables, when you create a variable v1 that is of 4 or L1, it's not an object, it's just a pointer to the object. Same goes for the elements of the list. And then when you modify a list, what we just did here, it does get copied, but it's so-called a shallow copy. So if the list is copied, but the actual element of the list are not elements, they are just pointers, and if the element is not changed, it will still point to the same address as before. So this is a kind of really important property, and it's like one way in which R tries to handle memory better. This was actually only introduced in one of the recent versions of R. I don't remember which number exactly, but previously all the copies, even from list, used to be like deep copies, and then they changed it to be like more friendly on memory. So this is an important property, and it also affects your logic and the thinking of the size of the object, of the size of the list, for example. What I mean by this is maybe best illustrated by the example. Let's say we want to create a vector of million random numbers, and it will have some size, right, in the memory. And then we want to create a list that will have this same vector in it 3 times. We create this list. And what you would expect is that the list will be like approximately 3 times the size of the vector. And when you check the size of these objects, which you can also do with another function from Lobster package, I will run both lines together. So when you check the size of the vector and size of the list, they're almost the same. And this comes from the fact that the list actually just contains pointers to these vectors, which are its elements. So in all, they are pointing to this same object as the one that you have in vector, and the only minor difference is because it has to be stored in a list, and this even empty list has to take up some memory, so then you end up with like maybe a few hundreds of bits of the difference. And also you can check the memory addresses and see that for all 3 elements in the list, they have the same address because they all point to the same object in your memory in the environment. So this is one important implication of this copy and modify behavior, of the exception of this behavior when it comes to creating a list. And the same rule actually applies to data frames, because you know that data frames are actually just a list under the hood. So the columns in the data frames are actually lists, and then when you create, for example, a data frame and you print it, so we create a data frame with 2 columns, 1, 2, 3, 4, 5, 6. And then when you think about it, if you want to modify a row of a column, for example, the first row, you would need to change both value in the first column and the second column. You would need to change 2 lists. And if you want to modify a column, you just need to change 1. So let's do this. Let's say we want to change the first column by adding 3. Oops, sorry, didn't copy it. Here I copy it explicitly just so that we can compare with the old object. So if I want to change the column in the data frame, and then if I look at the addresses, you see that the first one, which we changed, has a different address now, but the second one is still the same. But then let's say I want to change the row, and then I then copy the object and I change the first row by adding 1, for example, to each of the values. And then you see that both columns, both elements have to be changed. So because you are affecting both columns by changing the first row. So that's how it works for the data frames. And not quite the same thing, but very similar is happening with the vectors. So when you think of vectors, a character vector in R is actually drawn, so each element of the vector is drawn from a global pool of the all the possible unique character vectors. And then if you have a vector, for example, character, and you save it to some variable and you check its size. And it's like 220 bits. But then if we want to create a vector, a character vector that will be the same thing repeated many, many times, for example, 100 times, you can see that it's still, it's still containing the pointer to the same address. This is because, again, the real object is this unique character vector somewhere in the global pool of vectors, character vectors that R knows about. And then whichever character vector you create, it will always point to some of these unique character vectors. And if you repeat it, there's going to be just multiple references pointing to the same one and the same object. So this is another kind of way how R tries to be more nice on memory and use less memory for storing data. Apart from these kind of examples where the copying or modifying behavior still happens, but it's making shallow copies, there are some actual examples where R doesn't copy your objects when you modify them, and this happens, for example, with the environment or with the object that have single binding. So single binding means, as I explained at the beginning, binding is when you assign a name to the object, and the object has just one name. You would say, okay, why does it get copied? But the thing is, binding is not just the name. Also, when each function uses an object, it creates a binding to this object. So it's very difficult to predict when an object has one binding and when it doesn't, and so that's why it's just an exception in rare cases that it happens. In all other cases, R always makes a copies of things when you modify them, and then this takes time because it needs to make an actual copy. It takes time because it needs to allocate the space where this copy will be stored, and it needs time because it needs to populate this space in memory that it freed with the object that you created. There are some packages that you can install and use additionally that are usually implemented in C and that under the hood don't do this, so they can modify the actual object when copying it. And one of those is data table, and I will just show here an example. I will not go into details about it, but this is something that if you're interested, you can look up. So data table is kind of similar to data frames, and then let's say we want to convert our data frame that we previously created into a data table, and then we want to modify it. So this is just data table syntax for what we did before, adding one to the column of the data table. And then when we check the address of this other object, so this is the first one, and this is the second one, and then the same. What happened is that it was not copied, it was modified. So this is what makes it faster and more efficient, and so having all this in mind, I have here kind of so when you think about first thing that we did, first thing that we did, we called it V1, say V1 is V1, and then we modified, which means that we made a vector 0, and then pointed this V1 to this new one. What happened to 1, 2, 3? What happened to 1, 2, 3? V1 is now pointing to V1, sorry, to 1, 2, 3, sorry, to 1, 2, 3, 1, 2, 3. It would be very bad. It would be very bad if this object existing in our memory. So what is actually happening in our is if you expect overflow and if you expect overflow. Slow and slow and some people because this is running automatically, so this is running in the background, and there is a case where you should use it. So the garbage collector basically is running all the time in the background and is removing all the objects from your memory that don't have a binding. This makes memory more memory efficient. It also takes computational resources, because it has to run all the time in the background. It makes also tends to slow down the code. So this is something to have in mind. The topic of write your code and you are modifying data-oriented, and you should remember how to modify the column, this and I know that and by understanding this, you can write more. So this is kind of this would be the first part. This would be the first part, making introduction of. And when it comes to one other know how to use, and you should know how to use, and next would be our next section. There are no messages. There are no messages. Right. If you have any questions, write regularly. Try to check it regularly. So for the second part, I will talk about. So for the second part, and if you know something about program, and if you know something about programming, very often most programming languages, they can be labeled as either object-oriented, they can be labeled as either functional-oriented or functional. But what does this mean? Programming languages. But in very simple terms, in very simple terms, in object programming languages, this means everything is an object. In object programming languages, everything is an object. The main building block of the variables, methods, everything is variables, methods. On the other hand, in functional programming, objects, you still have objects. More like a functional style programming, more like a functional style of functions where essentials are taken, and they can also be treated, and they can also be data structures, as they can be assigned to variables. They can assign to variables. They can be in list or in any data structure that you have. They can be passed as an argument to other functions. They can even be output of the function. So when you have this kind of functions, they are often called primitive functions. That is what makes a language functionally oriented. And the funny thing is that actually in R you can do both. You can do object-oriented programming. There are actually 3 or 4 different types of object-oriented programming in R that you can do. But this is not something that I will talk about in this webinar. But if you are interested, and it might come in handy, especially if you are, writing your own package, you should know about these things. But we, in data analysis and in similar problems, in statistics, in biology, mostly use R as a functional programming language. And this is because most of the problems that we are facing, they can be solved in a way that where you split it in smaller problems and then use write functions that solve these problems. So this is kind of meant, and it's good. It's a good fit. So obviously you should know how to write a function. Why? You can ask why. Like you can have your code, you can have your scripts, you can have your analysis, it will still be reproducible. Why should you write a function? Well, because it's nicer and it's much better approach to programming. It's more systematic. So having a function that does something means having your code but doing something in one place, and it makes it, for one thing, it makes it more readable. It makes it easier to modify when some inputs or some parameters change. If you have nice or appropriate or good names of the function, then it's easier also for other people to understand what your code does. And you just eliminate the chance of making random mistakes and copy pasting when you're writing functions. So this is also another general programming principle. Do not repeat yourself. So you should not have the same code doing the same thing in several places in your script or in your notebook or whatever. You should always write functions instead. Okay, now that I convinced you that you should write a function, so how should you write a good function? There is also a thing that programming people say is that a good function should do one thing only. So you shouldn't have too long functions. They shouldn't be like 1,000 lines of code, and they shouldn't do all the analysis for your paper. It shouldn't be in one function. It should be split. One function can do one plot or can do one type of analysis, something, but you shouldn't do an overkill with it. So how, without further ado, without theoretizing, let's write like a simple function in R. For example, let's say we want to write a function that simply adds 2 numbers. And in R, this is how you do it. So the function has several important parts. The first one the name, or name of, just like any other variable, assign this to a name, to a variable. You can actually omit it. You can have a function without name, but let's, for the sake of overview, keep it like this. So we have a function that we will call addition, and we assign to this addition variable our function. In R, the function has first arguments within the parentheses. It can be one, it can be several, and it can also be none. And that's not really useful in general, but in this webinar, I will have a couple of functions that don't take any arguments. They're just for illustrating some examples. But in principle, then you have arguments within the parentheses, and then you have body of the functions, everything that follows after the parentheses. And if you have multiple lines in the body of the function, then you split it and enclose it within these curly brackets, like this, like here. And the final part of the function is environment. Now, environments are always a bit abstract, but it's a very important concept to understand also for the things that I will be mentioning later. So the environment, when we run all our code here, is the global environment. Then you see it here. If you are using again RStudio, you see it on the right, and you see what kind of variables you have in your global environment and so on. But the function also has associated environment with it, but you don't specify it explicitly in the code like you do with the name and with the arguments and with the body of the function. So it's automatically assigned to the function most commonly, and for all the that you will probably write, it will be global environment because you write them in the global environment. For example, some functions that you load from packages, their environment is the package. So this is also important concept to understand and to be aware of when writing and running functions. So we have our first function that does some kind of addition. So we might as well try to use it. I'll create the function and then let's say addition. Okay, if you type it, if you're using RStudio, addition, you can see when it suggests the function that it's a global environment. It will define in the global environment. So addition, and let's say when we call the function, we can give the arguments either by their names. So I can say x will be x will be 1, y will be 2, and I just run it, and I get the result. I could also just specify the argument by their position, which will also work. And this is okay for the functions which we use very often and which generally are known, and everyone knows what the first argument is supposed to be or the second is. But in principle, it's always safer to also the name arguments. Okay, we have the same thing here. So when you name the arguments, you can also change that order, and it will still work because they are named, so there will be no confusions. In our function that we just created, we need to specify both arguments. So if I wanted to run the function just with 1, for example, it would throw an error. It said the argument x, which I didn't specify here, is missing and it can't run. But you can define a function in a way that you don't have to specify all of its arguments. And this is by specifying kind of default value for some of the arguments. We have the example here. So if I want to modify the addition function, I want to create a function which will by default add value of 1 to any number that I give to it. So I write it like this. So when you are defining the argument, it says that the default value for the y here is 1. And then if we write that function, we can just call it just with one argument, but we can also give a different value to the other argument. And then this function, if I say that y is 2, this function will not be incrementing by step 1, it will be incrementing by 2. So that's useful also to know. And actually most functions that you use, you don't specify all of their arguments because they can have quite a few. Another important thing to know when you're writing function is that there is this special argument, these 3 dots, which is pronounced as ... and this argument means that the function can take any additional parameters. So this is especially useful if your function is calling within the body of the function is calling some other function. and then you want a way to be able to specify the parameters for this other function in your function call, but you don't want to copy paste all these arguments. So you can use the dot dot dot, and then this means that this function can take any other argument that it could take. So for example, we can write a function that will calculate the log odds of two numbers, x and y. And we also, when we are defining this function, we define that it can take more parameters, because the log function that we are using to calculate the logarithm in the body of our function actually can take a base argument. And we don't say we are lazy and we don't want to copy paste base, and we don't want to say, okay, I will define a parameter base in my function, and then I will give that base to this other function. So say, we just use 3 dots, and then this means it can take any additional argument. For example, then you can run it. You can specify any value of the base that you want, like base 2, base 10, base whatever. It might not seem useful here, but if your function that you were using has more than one additional argument that you want to pass, then it makes sense again, according to the do not repeat yourself principle. You don't want to copy paste all that. You can just use the 3 dots instead. So it's also can become very handy once you start writing functions a lot. Now that we covered kind of the basics of how to write a function in R, we can look at again how R executes them a bit under the hood, how your function calls get executed. So the first thing that I want to talk about in this part is the scoping. Scoping is kind of the opposite of what we talked about earlier when we were talking about variable. So variable binding means how a name gets pointed, how a name references a value of some value or some object in your environment. Well, this is the other way around. So when you call your function and you give it an argument, how does this function find this argument in your environment, in your memory or wherever? How does it find the actual value that it needs to use? And this process and the rules that govern it is called scoping. And R uses something that is called lexical scoping, and it has nothing to do with the lexical as in linguistic sense. It's not just lexical scoping. It's a set of rules that define how the variables are looked for and how are they defined. And the first one is that when you define a name inside a function, this is the first place that R will look for. So inside the body of function. If we look at the first example that we have here, let's say we have x defined in our global environment, and we say it's 10. But then we write a function, and within this function, we define x as 1. We define x as 1. And then we ask the function to return x. And what do you expect it would return? Well, if you know about scoping, then you know that the first place that this function will look for x when you ask it to return x, the first place where it will look is the definition of the function, and it will see that x is 1, and this is what it's going to return. But if the name of the variable that you ask for is not defined in the function, then it will go and look one level up, and this will be the environment from which you call the function, which in this case and most usually is global environment. And then if you have a function that doesn't define x within the body, and we call it, and it will return what we have defined in our global environment as 10. If, on the other hand, it doesn't find x defined in the global environment either, it will go another step up, and then it will look at all the packages that you have loaded, and then it will try to find the environment there. It will try to find the variable defined there in the environment of these packages, and so on. But this is not something that you should do. So this is how stepwise process in which R looks for the variables, and this is the first rule of the lexical scoping. The second rule has to do with the environment in which the function is executed. So all the code that we are running now, we are doing global environment, but everything that is inside the function body actually gets executed and the code gets run in an isolated. And what this means that whatever you create inside the function, whatever variables you assign or whatever, it's not seen from the outside, so it doesn't get exported to our global environment. It's just within the function. So, for example, if you have a function f2 here that assigns value 1 to the variable fa, and then we add the function to return fa. Simple. And this function works, and it returns 1. If we want to look for the fa variable outside of the function, so in our global environment, and we check whether it exists, if the function exists, you get false, because this variable was defined within the function, was defined within the function execution environment, and it's not available. You can't access it from the outside. This is actually very different and from what happens with loops. And when we come to the loops later, I will refer again to this isolated environment that the function gets executed in. And speaking of that, there are ways in which you can send your variables from within a function to your global environment. There is something called global assignment, but it's not a good practice, and I don't want to talk about it. I don't want to mention it. I mentioned it, but I will not show it, because it's not good practice and it's not something that you should do, because a good function should have no side effects. So you should not change anything in the user's environment, so somebody else will use your function. Maybe they have FA defined in their global environment as something else, and if your function overrides the FA and sends it to their global environment, you can mess up their code and mess up their analysis. So it's not a good practice, and you should not do it. And that's why functions are usually executed within the isolated environment. Okay, that was another rule of the lexical scoping. The second one, and the third one is the distinction between functions and other non-function variables. So I mentioned in the beginning of this part, this function part, that in R, functions are also objects. So they are special types of objects, but they are also objects. They can be assigned to variables, to lists, they can be passed as arguments, returned, whatever. But the good thing is that R can distinguish whether something is a variable or if it's not. And then if you have an object in your global environment, for example, we define a function called f3 in our global environment, and then in the body of another function, in the environment of another function, we define f3 as a number, as an integer. So we can do it because they are defined in different environments, so they don't get overwritten, because this is in global environment and this is in the function execution environment. But they are still the same name. They still have the same name. And so when your function looks for f3, what will it look for? The good thing is that R can make a distinction between these, because for the arguments of the function, it always looks for a non-function object. So if this function f4 is looking, in the end, what it needs to return is the f3 of f3, then R will know that this first bit is a function name and this is the non-function object name. And that's why this example will work, and you can run this function, and then it will return 11, because f3 is a function that adds 1, and it adds 1 to the f3 that we defined inside the function, so you get 11. So this works. It's a good thing that it works, but you shouldn't use the same names to define functions and non-function objects. And of course, you shouldn't name your variables something that you know is a function, like print or plot or sum or sqrt or something. You just should. It's a good practice to avoid these names. I will usually make a distinction, but sometimes it may cause problems. Okay, and the last rule of the lexical scoping is the dynamic lookup. So we talked about where the R is looking for the variable. So it first looks in the function environment, then global, and so on. But we didn't talk about when is R looking for the environment, for the variables. But what I mean is this. let's say we define a variable x as 15, and then we define a function that will take x and add 1 to it. And when you call the function, you think whether this function will look, whether the value of x that we ask in the function to add 1 to it, will it be defined in the moment when we wrote the function, where it was 15, and then it would return 16, or it will change if we change the value afterwards, after defining the function. So now our function is defined, but we change the value of x, and then we call the function, and we see that actually the output changes because R looks for the values of the arguments at the moment when the function is run, not initially when you create it. And this is called the dynamic lookup. And it's actually, so it's the last rule of the lexical scoping, but it's closely related to another concept that is important for evaluating or for running a function in R, and this is called something called lazy evaluation. I couldn't resist. I had to put a picture of Slot here. Because they say that a good programmer is a lazy man, and lazy evaluation is a thing that's happening in R, so why not? And what it means that so R will only look for the environment, also look for the variables at the moment when you run the function, but it will also only look for the variables if it needs to. So what I mean is this: if we have a function which takes two arguments, x and y, and the function just returns x, so we never actually even look for y. So what R will do, it will not care about y at all. R could be anything. R could be something that we didn't define. Y could be rubbish. So we didn't define rubbish. If you try to run this rubbish, you will get an error because it's defined. But if you try to run the function, which as an argument take this rubbish, it will work perfectly. You need to define the function. It will work perfectly fine because this y, which doesn't exist and which should throw an error, is never accessed from the body of the function. So it's really not important. And this is called lazy evaluation. So because R is lazy and it doesn't care about all the things that you put in there, if it doesn't need to access them at any point during the execution of the function, it will not even look for them. This is lazy evaluation. And it's another important principle and good to know. So now that we went through the major rules that define how a function will be run, one more last thing that I would like to mention about functions, and that is important when you're writing a function, is how to exit them. So how to return useful information to the user or to the person who is running the function when it fails, how to provide a useful message or when something unexpected happens. So for this, there are 3 functions again that you can use when you write your own functions. So when you want to exit the function at some point without finishing it, so when you want to interrupt it because it can't be calculated, you use stop. So for example, here we write a function that checks if our input parameter is numeric, and if it's not, it will exit with the error message saying that x is not numeric. Don't bother about if bit for now, because this is something that we will cover just in the next section. So it's for now, just the bit is important. So you return an error message and exit functions with the stop function, and you pass it whatever message parameter you want. And then we can run this function. If we run it with something that is not numeric, we get the message that we specified. But sometimes you don't want to exit the function, so sometimes it can still run and it can still finish, but you want to let the user know that something unexpected is happening, or just print some informative message of what the function is doing and so on. And for this, there are 2 other functions that you can use in your function definition, and one is warning. So it's kind of when something unexpected is happening, you send a message to the user with a warning, or when you just want to report whatever is happening, you use message, and they also take the character record, so whatever you want to send through. I think like why do we even need a different one? Is that message don't get stored, so you can't get to them afterwards. Whereas warnings, you can, so after the function has executed, and if it has produced a lot of warnings, in R you can check them by like typing warnings, and then it will print the last warning that you got. So this is the distinction between them, and this is an example of such a function that will print, that will again take X as an input and will check if it's numeric. Unlike before, now if it's not numeric, it will just take some random number, and if it is, then it will say okay, it's okay, and it will return X. And it's a stupid function, but just to illustrate the principle. And then if we run the function numeric input, it says that it's returning the input that is specified. And if we run it with the character, it says it's not numeric, and I'm returning something random, and then it returns a random number. So this is very useful when you are writing functions and you want to make them informative both for yourself when you use them afterwards, and especially for other people who will be using it. And that's pretty much all the introduction to functions that I wanted to do. The next topic that I will talk about is the control flow. In programming in general, the control flow refers to the order in which the code is executed. So variable assignment, function calls, etc., in which order they get run. And there are two main ways in which you can control this flow of code, apart from obviously putting some things before the others and choosing how you want to run it. And these are choices, statement of choices, such as if-else, and loops. These allow you to execute parts of code depending on the input, kind of conditional execution. And loops allow you to execute parts of code iteratively, so many times. We will start with choices. And the first, most obvious one is if. If statements, like there are present in, I guess all, if not all programming languages. In R, they have the following syntax, where you write if, and then you put condition within parentheses, and then you specify the action that should happen if this condition is satisfied. And you could also do, if condition is satisfied, you do one action, one piece of code, and else you do another action. Maybe the easiest is to just look at the example, and we can actually reuse the example from before, from our messages within the function. So it's the same function as before, and I'm going to just go through it to explain. So what it does, it's a definition of function, and it says if is numeric, the input parameter. So this is a function that checks if the input parameter is numeric, and I think it was covered in our previous webinar, and so it's just a Boolean operator saying like negation. So if the input parameter is not numeric, this is condition that the input parameter is not numeric. If this condition is satisfied, it will print a warning, and it will assign random number to X. So when you, again, as with functions, when you have multiple lines of code, you put them in the curly brackets. And then comes the else part. So else, or the opposite of condition, if the condition is not satisfied, it will just print a message saying returning X, and then the function will return X. So the condition in the if statement should always evaluate to true or false, to logical value. False in this case. And then depending on whether the value is true or false, either the first or the second block of code will be executed. Now maybe we can look at some more examples. So for example, what do you think would happen in this case, where we have value variable called val, and we assign it 10, and then we say if val, but val is not a logical parameter, val is a number. What would happen then? The thing is, if you don't specify something that's logical, I will try to convert it into something that's logical. And then for all the numbers, val is a number. For all the numbers that are greater than 0, it will be true. For 0, it will be false. So it will be kind of binarized. 0 will be false, val will be true, and then if val, it will print the value, and if not, it will say no input, and then this will print the value of 10 because it's converted to true. And what would happen if we pass it the character, for example? How would the R handle it then? Well, actually, you would get an error because R doesn't know how to convert characters to logical values, and then it says it's not interpretable as logical. So you should always pay attention to what kind of condition you write. Then we can, for the characters, for example, we could write if value if value equals my type is not working. If value equals val, and then this would be logical because we could interpret it logically, and then it would print value. So always, also with numbers, whenever you put in the condition, it's always good thing to explicitly make it logical, just so not to let R try to interpret it as logical, because then you might get some unexpected results in there. A few more examples of this. Let's, for example, what if we have not the vector of length 1, but 1 to 10, for example, as a condition, and then we say if length of x is true. Well, we should know this by now because this is length of x will be 10, and it will be converted to logical true, and then it will print not empty. But what, for example, if our condition is something like this, like numeric, then just empty numeric vector? What would happen? Length of x then would be 0. Oh, sorry, I didn't run it. So length of x now would be 0, and 0 would be interpreted as false, and then we would get empty. But again, it's better not to let R try to figure this out. Better to state it explicitly. Another case that might cause confusion is when you have a condition that evaluates to logical output, but its length is greater than 1. Then what happens? So, for example, if we have two numbers, and then R knows how to convert them to logical, and they will both be converted to true, but R will say, oh, okay, the condition has length greater than 1, and it will only be the first one. So it will run, but when this happens, it's usually not what you intend. So you don't do this on purpose. And then in R 3.5, there is this option to turn this warning actually into an error, and then you will avoid these kind of things. And it's a good practice if you set this environmental variable to true. So that would be the logic behind if or if else. And closely related to it is something called if else, which is basically a more compact and also vectorized version of its if. And it has the following syntax where you write it's basically a function, and you write if else, and the first argument is the condition, and then you have two more arguments where you can put here blocks of code that get executed when, depending on whether this condition is satisfied or not. Yeah, it's easiest just to look at the example, for examples. And if we say we have a vector 1 to 5, and then we say, okay, if x is less than 3, it will print less, otherwise we're going to print greater than or equal. And because this is vectorized, now you will not get the as before, where before R with just if else, R will be using just the first element. Now R will do this for every element of the X, or every every condition output that you have. So your condition is x is less than 3, and this actually evaluates 5 different logical values, but if else will work for all 5 of them. You will get the output, the vectorized output. Actually, the output that you get will always be the same length as what you have in your condition. But what you should pay attention to is that your yes and no vectors, like these things that you have as second and third argument, they should be of the same type. Otherwise, I will try to convert them to the same type. For example, if we say if x is less than 3, then print x, like return value of x, which is integer. Otherwise, return greater or equal to this character. What happens is that R will convert these integers to characters, which seems okay, no big deal. But if you need to use these integers afterwards in some calculation, it's a big deal. You will get problems because they are no longer integers; they are now characters. So always pay attention to make sure that your yes and no are of the outputs are of the same type. That's one tricky thing with if else, but there is another one. For example, it's the best illustrated again with an example. So let's say we define x as length of empty vector so before, and this will be 0. So it's something that will be converted to false. That's okay. But then we say if else. If x is true, you return 1 to 10, and if x is false, you return 11 to 20. And now you will assume that, okay, my x is 0, it will be converted to false, I will get 11 to 20. What you actually get is 11, because if else will always return the output of the same length as the condition. So this is another thing that you should always pay attention to, and this is another reason why I hate using if else, because I always make this mistake, and I always end up with some missing values. And like what happened is because the if else will always match the length of the condition in the output that experience, so, because it is vectorized. So it has its specific use, and it's good, and it's more compact and can make your code easier to read, because you don't have these long parentheses like several lines or whatever. But you should always pay attention to it before you use it. Apart from if else, another more compact alternative to if else conditional that we saw in the beginning is switch function. And whatever you write if else, you can also rewrite switch, and I'm showing here with an example. For example, we define x as a, and then we can write this long if else statement saying if x equals to a, then we will return this. If x equals to b, we will return something else. And else if x equals to c, we will write something else, blah blah. Or if it's nothing of this, we will stop the execution and we will return the error saying that's invalid, x value. And it's kind of bulky, and there's a lot of if else there. We can replace it with a more compact switch statement in which we just write again in the first place our condition, so it's x, and then we just list options that we want to use. So if this condition, if it's a, we want this option, b this option, c this option, and in the end, if it's none of them, we throw an error. That's how okay. To show that it works, we have x, and we define it as a, and we get option 1. And with switch, we get the same thing. And switch has, apart from it being more compact already as it is, because it is actually the function that's a copy of the function or implemented C function, I think. It has the same interesting property of propagation, super lazy. And if you want to have multiple options that evaluate to the same thing, you don't need to specify all of them. You can just write A, B, and then if it's empty, it will just take the next value. So this is the same. So you can say A and B, I want them both to be option 1, and C, I want to be option 2. I don't need to write this option 1 twice. I can use it just once. If it's super lazy, it's super useful. and you get option 1 because we define Rx as A. With switch, you should pay attention. Like with if else, you don't need to cover all the options. With switch, you should always make sure that if you don't meet any of the options specified, that you return an error with the stop into. So the last option should always be stop. Otherwise, the function will return null, and then again it will not throw any kind of error, but it will not be the output that you expect, and you might run into problems later somewhere in your code if you're using the output of this function. So if else separately, if else as in vectorized, and switch are the three ways in which you can control the execution of the code code flow in your R scripts, and they allow you to execute parts of code conditionally on the input, depending on the input that you have. And another way in which you can control the flow execution is with loops, and loops allow you to execute part of the code iteratively now, so many times. And loops have kind of, they are also, you have them in all programming languages, but in R they have kind of a bad reputation. And if you ever were trying to learn R and you were probably taught that you shouldn't use loops because they are slow and they are horrible and they are like part of the R inferno, as they refer to them in one book. That's actually, loops are not super slow and super bad per se. It's just that they are flexible. And what makes them slow is this underlying behavior of R, actually, with this copy and modifying thing and the binding and the stuff that I mentioned in the first part. And because when you try to do this many times, when you try to copy your data many times within the loop, this gets slow then. But they're not bad per se, and it's not that you should not know about them. So the first kind of loop that I want to talk about is a for loop, and they are used to iterate over some number of items. When you know the number of items that you want to iterate over, in R, they have this syntax where you write for, and then in the parentheses you say item or I, or it's one item, in, and vector is the vector or list of element that contains these elements over which you want to iterate. And then you say perform action. This is some code you want to execute for each item in this vector, for example. Like the most stupid example that there can be, or we write a loop which say for I for each item. You can call it what you want. For I in this vector 1 to 3, print I. And what happens is that you get 1 to 3. That's how loop in R works. Note again, as all these previous examples with the functions and the if statement, everything, whenever you have code split on multiple lines, you put it in the curly bracket. The thing is, with the loops, one important thing to know, and one important distinction between loops and function, for example, is what I mentioned earlier, is that the function gets executed in its isolated environment, and this is not the case for a loop. So if you have a loop, and it can access whatever it is in your global environment, because it will, like, the function will first look within the function body and in the function environment, find the variable that it needs, but loop doesn't do that. Loop is in the global environment, and it will override whatever you have in the global environment. So you should be careful with it. So for example, if we define I is 20, and then we say in our loop, okay, let's iterate over 1 to 3, and let's call it this element I, and we say for I in 1 to 3, print I, and you get 1 to 3 as we did before. But what happens is that our I got actually overwritten. It's no longer 20 as we set it in the beginning, because this iterator was first 1, was then 2, and then was 3. And this was not happening in an isolated with that function. This was happening in the global environment. So it's not unimportant how you name this iterator, because it's not only used, it might seem that it's only used within the loop, but loop is not included in an environment. That's the important thing to have in mind when you run loops. In case you want to exit, if you want to check for some condition whether it's true or false, and if you want to break out of the loop, there are two ways in which you can do it in R. One is the next, which will exit the current iteration, and break will exit the entire. Like easiest again to explain with the example. If you have loop that is iterating over integers 1 to 10, and we say if the iteration, the iterator, let's call it iterator, the number of we are iterating in each iteration. If the iterator is less than 3, we go on and we print I. If the iterator is greater than 5, we want to break out of this stupid example, but just for the purpose of showing. So if we say if the iterator is less than 3, we want to break out of this iteration, and we don't do anything. And then it increases to 2, and then we break out. It is still less than 3, and then it increases to 3, and then it's no longer less than 3, and now we execute the remaining of the code and say print I, and then 3 gets printed. Then it goes on to the next iteration, and it says 4, okay, it still satisfies this condition, gets printed. 5 also, but then if greater than 5, we say break, and then the whole loop terminates. That's when and we get the output just 3, 4, 5. That's in principle how the loop works. I think with all the examples so far, we were always just printing our output to the console or to notebook or whatever. And that's not really useful. We usually want to save the output of the loop, of each iteration of the loop, to some variable. That can be list, it can be data frame, it can be matrix, it can be whatever you want. But the thing is, you need to specify this before you run the loop. If again, we can look at the example. Let's say we don't do this. If we don't specify where we want to save, if we don't make the object to which we want to save the output of each loop iteration, we will get an error. Said out is not found, because you enter the loop and then it wants to save something to out, but it can't find it. That's why usually before we need to define, like, for example, empty list in this case, called out, and then I go into loop, I iterate over integers from 1 to 200,000 and save for each iteration in this list at this position a random sequence of 1000 number sample from uniform distribution. That will work then. It works for a while. The thing is, this is not really a good way to do it. Because here we specified an empty list, and then we entered our loop, and for 100,000 iteration, we were increasing our list, which initially was just an empty list. Then in the first iteration, we increased it. We added one element, and then we increased it again, added second, and so on and so on. And this is not a good practice in R, because what R actually does is related to the modify on copy behavior that I talked about at the very beginning. Is what R actually does is it needs to create copies of all these. When you add one element to the list, it creates a copy of the list. But not just that, when you create your list and then you want to add an element to it, what it first needs to allocate the space for the new object, and you need to copy the original object to this new space, and then the garbage collector that I also mentioned before runs and clears this old object. So it's like three computationally intensive processes that executed in each iteration of the loop. And you can see why the loops have such a bad reputation, because this will take time. One better way in which then you can do it is to specify a list or whatever you're saving your output to in the beginning to make it of the size that you need. So for however many iterations you're going to do, is you create a list of that length. And you can do this with a vector function, when you can specify the mode of the vector and the length of the vector. And this will now be the empty list, but it will already be 100,000 elements long. And you will save this step of allocating new memory for each iteration of the loop, and your list grows. And then this will be a bit faster. Okay, you don't need. Oh, something happened. Sorry about that. We lost our environment, but that doesn't matter. Reload the packages again just in case. Okay. So you should pre-allocate the space for your list that you are saving to before, and then you will make it. It will make your execution a little bit faster. Where were we? Yes. We can benchmark these two options. Just also to see how you can measure time in R, time of the execution of any of the processes. So there is a function called system time, but I prefer to use a more flexible one with more output, so-called micro benchmark from this micro benchmark package, which we loaded before. And because here you can specify your chunk of code, and you can specify, for example, how many times you want to run the code to determine how long it will take. Anyway, I'll just say to do it once, just to say one time. Okay, and when we pre-allocate our space for the function and we measure how long it takes, we get the output. So this is the minimum, maximum, median, blah blah. They're all the same now because I only did one iteration, but they are the numbers in microseconds, I think, of how long it took for this function to finish. And then if we do the same thing we do the same thing, but if we don't pre-allocate the space, so we use just the empty list and calculate. And you can tell it's going to take more. Actually, we'll crash our R session again. Anyway, don't do it. Take home message. Don't do it. Always pre-allocate the full length or the length that you want to use before, and don't grow it on the go. So this is for the for loops, and they're useful when you know the number of iterations that you need to do when you're iterating over something, over some vector or some list. There are two more alternatives, two more loops that you can use in R, and there are while loop and repeat loop. While and repeat, both you can rewrite whatever you wrote with if loop, with while and repeat, but they are different in the sense that with while you iterate until some condition is met. So the syntax of this is while, and then the condition you need to evaluate true or false, and while it evaluates true, you do some action. So for the example, if we define our I as 1, and then we say while I is less than 5, we will increase it. We will add 1 and we will print. And this will go on all until we reach I5. And then you get 2, 3, 4, 5. For the repeat, you could do the similar thing, but then the syntax is a little bit different, and you write repeat and some action, and this will go on indefinitely. So you need to include some kind of a conditional statement, one of the conditional statements that we saw before, and you need to say break. So you need to define within the loop when you need to exit from the loop. And the same thing you can execute with the repeat loop, and it will print the same values. In principle, so you can see that you can replace any with the while or repeat loop, but why you shouldn't do it is because they are more flexible. Because they are more flexible, you can replace them, but flexibility in general is not a good thing in R, because flexibility means that R can do many things, and it needs to decide what it will do, and you should avoid this. So because repeat is much more flexible than while, and while is more flexible than for. R will spend time deciding what it will do, and this is also why they say you should not use loops. You should use functions like lapply, apply, and similar that I'll be going to cover in the next part. also because they are less flexible than the loops. They are specialized for some purposes, and then they are a bit faster to execute. I think I heard that there was a question, Mystic Mike was asking what other objects could benefit from free allocation, and with this also apply to more complicated data structures like data frames. Yes, all the objects will basically benefit from free allocation, because this is not specific for the object. It is about growing the object. So the data frame that you mentioned, you could save the output of your loop, for example, to data frame, but then you would need to cbind or rbind the output of each new iteration, and you would basically need to grow your data frame in the same way you are growing list or whatever. So all the objects benefit from pre-allocation, because you avoid this step of in each iteration allocating a freeing the old memory and allocating. You avoid that step, and the function your loop runs somewhat faster. So yeah, any kind of object, whatever you can think of to save your results to, basically. And with that, I think that would be enough about loops for now. We will come back to them later. But now I would like to talk about the functionals, which are labeled or advertised as a better alternative to loops in R. So in general, functionals are just functions that take another function as an argument. And we actually already saw and already wrote one example of functional when we wrote our function that was calculating global ratio, and then it was we didn't give it the function as an argument. So in R, we have a specialized functional that are meant to replace loops, and they are in the base R. They are the ones that I'm going to talk about. There are others in the packages, but I will not go into this. You can look them up. You can refer to the reading materials that I have in the end of this document. But in the base R, there are so-called apply family of functions or functional that are meant to that are kind of faster than loops and do the similar things. And why are they faster? It's mostly because they are specialized and they are less flexible. What it means, for example, apply, which is the basic function in this group of this family of functions, is specialized to work with matrices or with higher dimensional objects like arrays in R, be 3-dimensional or 4, 5, and whatever dimension. And then you have also lapply and sapply and a couple of others with different specifications that are used to work with 1-dimensional. So vectors and lists, they iterate over 1 dimension. Not to theorize too much, maybe it's easier to look at examples. And for the first one that we look at is apply. So you can think of apply, what it does. So it works on 2-dimensional arrays on matrices, and what it does is summarizing the rows or the columns of a matrix, for example. So it takes 4 arguments. The first one being the matrix or the array that you want to iterate over. The second one, margin, is an integer argument specifying over which dimension of your array or matrix you want to iterate. So for matrix, which has 2 dimensions, you can specify either 1 meaning rows or 2 meaning columns. For 3-dimensional, 4-dimensional, you can go on. You can specify also more than 1 margin to iterate over. And then you give the function which you want to apply to each margin of this element x. And the last argument is the 3 ... that we mentioned earlier. It means in this argument you use to pass any additional argument to this function that you are using for summarizing the method. So let's look at the example. For example, if we have a matrix with 5 rows containing numbers from 1 to 20, and what we can do with apply is to apply some function over rows or over columns of the matrix. So basically to summarize this matrix either by rows or columns. So we could, for example, calculate the mean of the rows by saying 1 and using the function mean. Then we would get a mean value for each row. What we could do instead of using some function that we wrote before that we loaded from a package from Bezier, we can write an anonymous function. So this is a function that is not assigned to variable. If you remember when we started talking about functions, that I said the name is optional. And there are cases like this one where you don't really need a name for this function because you only use it within apply. You don't want to save it or anything, so you just write it as an anonymous function here, and you say, okay, function that takes x, and I will add 1 to x. I want to apply this function to the rows of my matrix, and you get the output. But the interesting thing now, if you pay attention, you can see that our initial matrix used to have 5 rows, and the output that we got has 4 rows and 5 columns. So something happened there. What happened is that the apply function takes each row and applies the function that you specified to it. But then when it returns the output, it returns it in columns. So now here it returned the output of each iteration, let's call it iteration of this function, is adding 1 to the row. And then the output of the first iteration is this. The output of the second iteration is this, and so on and so on. And it just returns transform. So if you're using apply, and if you're turning if each iteration of your function applies returning a vector, you should pay attention to this transposition of the matrix that you get. So you get the transpose matrix as an output. You could also, as I mentioned, you don't need to specify just one margin to iterate over. You could specify 2, which in this case is kind of useless because you're just basically here. What I'm saying is iterate over rows and columns. In the case of matrix, it means iterate over elements, add to each element 1. And then I get the output matrix with each element increased by 1. We could just as well apply to 3-dimensional arrays in this case, and then I wrote a 3D, but it's actually it's okay. 3-dimensional array with looks like this. So if you're not familiar with arrays in R, they are kind of stacked structure, and it has like rows and columns like each matrix. A third dimension, which here is shown one below another. So this is kind of the third dimension of an array, and then you can apply this. You can apply a function to, for example, in this, if you specify 1, it will apply a function to all the rows of this array. So all the rows here and all the rows here, and in other dimensions, so it will just use rows. And get the output because each, if you look at it again, each kind of matrix had 2 rows, and then you aggregate all our rows and you get 2 means, 1 for each row. You could as well apply this function to 2 dimensions of say rows, but separately also in the third dimension, and then you will get again in the columns the means for all the rows in each separate matrix, which in this case is a third-dimensional array. Right. When you increase dimension, it becomes increasingly complicated to keep track of what you are applying over which dimension, but it can be useful if you are working with this kind of data. So that would be apply, and that would be iterating over n-dimensional structures in R. All the other functions from the apply family, they iterate over 1-dimensional structures, so vectors or lists. And in this first group that I want to talk about is the main one, the major function is lapply, short for list apply. And just like apply, it takes the x function list of vector of elements that it will iterate over. In this case, 1-dimensional x. Previously, it was more dimensions. And the function that we want to apply over each element of this in this X, and the all additional argument that you can pass to the function. And then just let's look at the simple example where we have a list, and the first element of list is sequence of integers from 0 to 10. The second one is the random sample numbers, 10 numbers from 1 to 100, and the third element is random 10 numbers from uniform distribution. And we want to apply to this list mean, function mean. So calculate mean of each of A, B, C. It's pretty simple, and we get the means. It's better. It's better when you would use this rather than applies. Obviously here because you have different. If you have, for example, different lengths of arguments or whatever you have in the list that you can't fit in the data frame or in the matrices, you would use lapply for not apply. Very closely related to lapply is sapply. S here stands for simplify, and the only difference actually is that this function attempts to simplify the lapply output. So in the previous example that we ran, lapply returned the list, and if you use sapply, it will always try to simplify this. So if you have a list, it will try to make a vector of it. If you have an array, it will try to reduce another dimension, and so on and so on. And this is controlled by the additional parameter that sapply can take, is simplify, and by default it's set to logical true. You can set it to false, and basically get lapply. And it also has another logical parameter, use names, which controls whether the names of the input X per argument, so the thing over which you iterate, if it has names and you set use names to true, they will be preserved in the output. Or also if X is a character vector, then it can use just this X as the names of the output. And if we run the sapply on the same example as before, we get the same values, but now they're not a list like before. Now they are a vector. So the output is kind of simplified. This function is generally advised against using it, and if you are writing a code that needs to follow some guidelines or something, it's very likely that often they will ask you to not use sapply, because it's a recurring pattern. Whenever R, in this case, R needs to infer how to best simplify your output, it can produce unexpected results. So it's often better not to use it. And if you want to simplify a result, you can do it yourself after calling lapply. You can call unlist or whatever. So sapply can cause problems. If you don't want to use sapply, you can use another alternative. So if you don't want to use lapply, there's another alternative to apply that out there, and it's called vapply. I don't know if I'm pronouncing it correctly. Vapply. The only difference between vapply and the sapply is that you need to explicitly say what kind of output you expect from your function, and you do this by using this fun value argument. And this should basically be an example of the structure that you expect each iteration or each time you apply function to one of the elements of X, you expect to get this kind of data. So this structure, this class and this kind. Maybe again easiest to illustrate with an example. So we define fv variable as a vector of mode numeric of length 1. So just a numeric vector. And we say when we iterate for our vector v, which we defined earlier, so the list v, which contain vectors of different integers of numeric values. And when we apply the function mean to each of these elements, we expect to get this output. We expect to get the numeric vector of length 1. So the value of this actual vector doesn't really matter. And what the function, what vapply will do is it will just check whether each time you run, each time it runs function on the one of the elements v, whether it gets the same class and the same length as an output. And then you get and you get simplified result, but you are sure that this output is going to be of this class. That's why it's better. It's kind of better and more safe approach than the sapply. You may think that it may be tricky when the function that you are using outputs some weird class or weird not one of the basic data types in R. For example, function summary. It outputs a table object which also has a property of class summary table. If you run class of this S3. Class of F3. See that this is summary default and table. This is kind of the class, but you can still use the vapply when you expect this kind of output. You just need to provide one example of this output that you expect. So you can just run the function that you want to apply elements. For example, first element, and you say, okay, this is what I expect, and you pass it to the vapply, and then it produces your output for all your three simplified output for all your three iterations of the factorial. That's vapply, and it's a better alternative to apply than sapply that is here. But this is not everything. So there are additional functions in the apply family, and each of them they have a very specific use. And this makes them faster, like I mentioned already before, because they are specialized for some use cases, and you only use them for these use cases, and they don't leave much space for R to try to guess what you're trying to do. The first one of those is tapply. So tapply, you can think about it as kind of a multimodal version of sorry, not really. So tapply is like a grouped version of lapply. So whereas in lapply you apply your function to each element of the list, you may be in a situation where you want to group the elements in your list and then apply some function to each of the groups separately. This is when you use tapply. It is best to show it again with the example. For example, if we have a vector of random 100 numbers sampled from uniform distribution, and we assign them to three different categories here. A, B, C is what you get with these letters input variable. So we sample these letters, 100 letters, and then they correspond to these 100 numbers that we sample. So we kind of assign each number to one category. And then we want to calculate something, for example, mean for all of these categories. We pass X as the first argument, then we pass the grouping argument as the second, and then the function that we want to apply using tapply, and we get the mean for the three. So even though our vector had 100 elements, we get the mean calculated for these groups of variables. And this is actually really useful function. It saves you time, saves you don't need to type manually, separate your input list into three different lists and then apply a function to all of them. I use tapply. And it's kind of an example of how a specialized function in R can be really useful. And then there's another one in the apply family called mapply. And this is what I was starting to talk about and said that you can think of it as a multi version of lapply. What this function does is it takes any kind of number, any number of lists or vectors that you want to iterate over, just that they have to be of same length, and then it applies the function that you want to apply to first element of all this, to second element of this, to that element, and so on and so on and so on. So it's kind of a multimodal approach. It has a little bit different syntax than the one that we saw before, because the first argument that you pass to it is the function that you want to apply, and then you put the tree with the dot dot dot. You pass all the lists or all the vectors or all whatever you want to iterate over, any number of them. But previously we used these 3 dots to pass additional argument to functions. Since now we are using these 3 dots to pass the element, to pass the structure that we are iterating over, we use more args argument to give all the other arguments to fun. But now you need to put them in a list, because they're just one argument, and pass it. And then you have again the option to simplify and to use names just like we saw in the sapply. It's maybe a bit abstract, but once you figure it out, it's also really useful, and it's really for specific use cases. So for example, let's say we have 2 vectors. We have vector 1 to 5, and we have vector 3 to 7, and then we want to sum the first element of both of the second element, and so on. And we just use it with mapply. We give the function and all the elements that we want to iterate on, and it does this for us. It's also super useful and good to know about. And you'll be happy to hear that there is just one more that I want to talk about. Just one more function in the apply family, and this one is called rapply. Like R here stands for recursive, because what it does, it takes your list, which is usually is a list that you want to iterate over. It can, because lists can be nested, and you maybe want to iterate over all elements of the list that are not list, and this is where you would want to use rapply. So what it does, it takes this object, which is now called for some reason object and no longer X, but it's a similar thing, and it applies the function, which is now F, given argument F, applies functions recursively on each element of this list that itself is not a list, so that's why it's recursive. And you can also specify classes, and then it will apply this function to each element of the list that is in these classes. So you can specify multiple classes. So if it is in one of these classes, it will apply the function to this element. And if it's not, you can specify this argument how. So this is specifying how to treat all the other arguments that the functions will, all the other elements of the list that the function will not be applied to. So you can set it to either replace, in which case they will be just kept as they are, so they will be propagated in the output, or you can specify some default, you can say list or unlist as how, and then they will be replaced by whatever you specify as a default value. It's again maybe a little bit difficult to wrap your head about just like this, but if we look at the example, it will be easier. So we create a list in which we have the first element is a numeric vector of random number of samples from uniform distribution, and the second element we have the character vector, and the third element we have, and then let's say we want to apply the function mean to all the elements of this list, which are either integer or numeric, and the other ones we want to keep as they are, so we want to propagate them in the output. And we do it like this, and you can see that the first element, which was numeric, now the function was applied to it, and you got the mean. These other two were kept as they are. So in the output, they were just replaced by the. That's why it's replaced. Alternatively, you could do the same thing, but say I want to replace all the elements that I can't apply the function to. I want to replace them with something. Say I want to set them to NA because I don't want to use them afterwards, and then you just set the default to NA, and then they get replaced by NA. This is done with specifying list as a value of how argument, but if you do unlist, what it will do is just simplify it, just unlist your output, but it's basically the same. So this is how rapply works. It's maybe the most convoluted and the most specific of all of them. It's useful if you have a list containing very different kinds of data, and then you want to apply something to just one type of data, but you don't want to first filter your list. And why wouldn't you want to? Well, because of what we talked about initially, like when you modify your list, you actually making a copy. So, and then you would apply function to the copy. So why not just do it at the same time and you use apply for that. So this is how you should the use case in which you should use apply. So there's been quite a bit of applies. I think they are useful and you should really use them, and they are faster than loops. It's true. Whatever you were told when you were starting to learn R, loops are bad and all that, blah blah blah. Makes sense. But even with applies, you will still probably run into situations when you will be frustratingly pulling your hair out. Why is my code so slow, and what can I do about it? And I'm using applies and I'm using all that, and it's still slow, and there is no way to do it. Well, it's good to know that there is one more thing that you can resort to when you are not desperate, but when you want to just make your code run faster. And this is kind of the brute force. It's the parallelization. So in all programming languages and in general in computation, when you want to make something faster, the most straightforward way is to parallelize. So what it means? It means that you allocate some resources, some computational resources to each iteration of your loop or your lapply or whatever you have, and then the iterations are run. Some of them or all of them are run simultaneously at the same time. So the second iteration does not wait till the first one finishes. You run them in parallel, and that's why it can be faster. And this approach of brute force parallelization, of how it's often referred to as embarrassing parallelization, it can be very useful and very often applied in science and in the problems that we are dealing with in data analysis, because very often the different iterations don't depend on one another. So they only need to be merged in the result, like when you output the results. So it's really applicable and it can be used often, as long as you have, of course, enough computational resources that you can run things in parallel. Here I will show you a couple of ways that you can do parallelization in R, that you can run functions in parallel, and I will show you the equivalent of the lapplies and apply family functions and the equivalent of loops. How are they run in parallel? I will not go into details because it's a really complex topic and it would merit a webinar of its own. But just as a starter, this is how you go about it. So you would need to use one of the packages that allow parallel computation in R. And if you want the parallelized equivalent of lapply, you can use the function mclapply from the package parallel. So load that package. And mclapply looks very similar like lapply. So it takes the x argument that contains, it's like a vector or a list that contains element over which you want to iterate. It takes a function that you want to apply to this argument, and it takes ... with which you pass other arguments to this function. So everything is the same as in lapply, but then it has quite a few other arguments which specify how your function will run in the parallel environment. So they all start with MC, and the most important one is MC cores, which MC cores specify how many processor cores you want to use to run your parallel calculations with. And you should take care with this because you don't want to first, you need to know how many of the cores you have available, and then you don't want to assign all of them to your R process because the other processes running on your machine will suffer, and you will likely block everything. So you can check with the core. Second. I blocked check the number of cores that you have available on your machine. Did I load the packet? That's detect cores. detect cores from the package parallel will tell you how many virtual cores you have on your machine. If you also give it an argument logical and you set it to false, it will tell you how many actual physical cores you have on your machine. So this is not the data from my machine because I'm running it Studio Cloud. This machine has like 16 of them, and then you know how much you can work with and how much you can allocate to your R processes. So other than that, using MCL apply is very simple. You just, again, we'll show you an example. You take your vector that you want to iterate over, and then you just use the same syntax as lapply. So you find the function that you want to use, you say how many cores you want to use for this, and you run your function to get your results without actually doing anything much in terms of parallelization. Because MCL apply basically handles for you. So it uses this forking system for assigning assigning processes to different cores. And this is all done under the hood, and you don't need to do anything, which is great, but it only works for Unix-like systems. So that's why you will not be able to do this on Windows. I mean, you will, but you can only specify MC cores 1, which is basically a sequential execution, and you just don't have any parallelization left. One major difference between this function and the normal lapply that you use sequentially is that here you will get results even if some iterations of the model, even if for some values it fails. So if for some values that you're iterating over. So that's why it's always important to look at what kind of results you got, because you will not get if you run just lapply, and if it failed in one iteration, you will get an error, you will get no results. Here you will get results because they are calculated on separate cores, and sometimes in separate machines, and you will get results. But you need to inspect them. So let's look at the example where we are here, for example, iterating over 1 to 4, and we have this function where we just say, okay, if it's the third iteration, throw an error, otherwise return success. And if we run this parallelly, we get a warning, kind of warning from the MCL apply function, so not the warning that we wrote in the function, saying that one of the cores encountered problems and the values of the jobs might be affected, but we still got our results. If you check results, they are still there. But the thing is that one of them is not what you expect. So one of them has a different class. It's saying like, okay, its class is try error, and in this iteration, the execution of the function failed. Basically, it's easy to see it now when we have 4 iterations and all of the character vector of like 1, but you really want to expect this also when you're iterating over many more values, and you have a bigger outputs, and you can just check the class of the outputs and look for this try error class, which is a specific class object that you will get when your execution in one of the iteration fails. So that's in short, very briefly, how you can use MCL apply. And obviously you can't use it on Windows, but for people running on Windows, luckily there is an alternative. In the same package, in parallel, there is this parallel apply function, which works very similarly to MCL apply. The biggest difference is because this function uses a different mechanism to assign your processes to parallel workers. And this is using something that is called sockets. And this is available on Windows, but it's a little bit more not complicated, but you need to explicitly specify more things than you did with MCL apply. So MCL apply did everything for you. You can really just run it without knowing almost anything about parallel computations. But here, what you need to do, you need to explicitly make create a cluster. Again, super easy. You just use the functions from the package, and you, same as before we used to specify number of calls that we want to use in call to the functions. Now we need to, before running the function, make this cluster and kind of reserve it for our computation, and then we say, okay, make a cluster, save this to some kind of variable, and this variable will be the first argument that we give to parallel apply function cluster that we created. What we also need to do is to export variables from our global environment to the cluster, because this cluster can be, so if you are using a server or something, can be a different computer or something, and you need to export your variables, sometimes in your packages, what is in your environment and you want to use, you need to export it to the actual core that is going to run this computation. And in theory, you need to do this with MCL apply as well, but it does this for you under the hood, and you don't need to worry about it. Here, you need to explicitly say cluster export, and then say to this cluster that I just created, I want to export this variable v. And then you can run your function in parallel. So it's also again very similar to lapply, except the first argument now is the cluster that you're using, and then you give the vector or list over which you're iterating, and then you give the function. And the important thing is you also need to stop the cluster after you finish it. But in principle, again, not super complicated, and it works, and you can run it and you get your results. So quite nice, quite neat, not much trouble. So this is how you parallelize lapply. There is also parallel apply also has a function par sapply, but it's the same thing with sapply. You don't need to use it. It's better if you explicitly simplify the results afterwards if you need. When it comes to loops, if you want to parallelize your loop, there are two other packages other than parallel that you need to use, and these are called for each and do parallel. So for each is just a package that provides like iterating functionality that iterates, and do parallel is kind of an interface between for each and parallel that we used before. And with these two, you can parallelize the loops. With this, you can use either of the approach that we saw earlier to start a cluster, to kind of register the cluster. You can do it explicitly, like with lapply, what you need to do on Windows, because alternative. So you again do the same thing. You register the cluster, and you if you need to export something, you export it, and then you need to stop it after you run it. Or you can use just the same thing as MCL apply. You can just specify the number of cores, and then you do it with register to parallel, and this basically then takes care of all these things for you, just like MCL applied it. You just give it number of cores. I don't know why I took here. I can use this for like everywhere. It doesn't matter. This is how you start and stop your cluster. And when it comes to actual looping, the syntax is similar to for, but not quite the same, because for each is a function, unlike for is like a condition flow operator or whatever. Here for each, you say for each, and then you give the variable over which you want to iterate. Name like iterator is again like in for I, or it can be like whatever, and you set equals to variable over which you want to iterate. This will not this doesn't mean that I will be overwritten with v, but it means that I will be each element of v in one iteration, and then you use this do par operator, and you give whatever function you want to run on each iteration of this vector that you are iterating over. The thing is that for each can also take additional arguments. So because it's function, unlike for, it will output its results, and you can just save variable like var or whatever. So you don't need to make a list beforehand or make whatever data structure you want to save each loop iteration to. So it's kind of a loop, but it's also a function. And it can take additional arguments that say how you want to, for example, combine your output Do you want it ordered? What do you want to be the first and the last value to be passed to the argument? You can multi-combine it if it comes from different machines or whatever. So there's a lot of arguments which you can modify them, and I go into detail because it's out of the scope of this webinar now. But in principle, those are the most important things to keep in mind when you want to run your loop in parallel. And again, it's pretty simple, pretty straightforward. You get your results easy. Same thing with registering cluster implicitly, like we can do on Unix systems and not on Windows. So this is how you do the parallelization, but the big question that you need to think about before you do anything, whether it's worth to parallelize or not. I will just show it on this one example, and then I will explain afterwards. So here have an example of a function that will calculate a confidence interval of some statistics like mean, median, whatever by bootstrapping. And I have the sequential version. It's a function that does this sequentially by calling the normal sapply and iterating over the argument which is passed to the function to define the number of iterations. And then it calculates median, like bootstraps, calculates median by something from the median value that you have. Let's say these are some median values of something. And you want to calculate the confidence interval for this, and you do it sequentially with this function. And then also I wrote a function which you can do parallel. So just instead of using sapply, we register the cluster, export our variables, and we use our sapply to do the same thing basically. Let's run these two functions and try to measure how much time each of them will take with micro benchmark, which I also told you about before. And I said again, I didn't load it. Micro benchmark because they are crashed. So and we get our results. And what you can see when you look at the numbers. Sequential function, this is our parallelized function. This is minimum same distance that it took to calculate this, to run these functions, and they're all the same because we only did one iteration. But what you can see is that actually the sequential function is faster than the parallelized function. And you are like, why? What happened here? Well, the thing is that it also takes time to create cluster, to assign your jobs to different cores that are going to run them, and then in the end you also need to merge your results. So all of this takes time, and if the computation that you are doing is not comparably longer and doesn't comparably much more time than this merging and splitting processes, then these things will kind of outperform they will take more time than the actual computation, and you will be adding extra time to your calculations. So the most important thing is actually to think whether the thing that you're doing really needs to be parallelized or whether you are just overkilling it. And another thing that you of course need to have in mind is the memory, because when you're running something sequentially, it's much easier to control the memory that you're using, whereas when you're running things on parallel, and if your task is memory intensive, some of the workers might die, just the calculation will not be performed. And for example, in the case of loops in parallel, you will not get any error or something because the worker will die and you get just null in this element, and then this might again confuse you and your result because you don't get an error. You think everything is fine, whereas in fact you're getting your work dying because of not enough memory, and you are getting wrong results. So this is like two things that you really need to keep in mind when you want to run things in parallel. And that's about it about parallelization, and that's about more or less it from what I wanted to explain in this webinar. And as promised in the beginning, I said I will finish by just telling you some tips and tricks that you can apply without much thinking, not without much thinking, you need to think, but that you can apply it like out of the bag, make your code faster. So I'll just go through this. So always use specialized function for any specific task that you have. Just like functionals with applies, applies and stuff, it's always better to use something that is specialized for this function because it's usually better implemented and it leaves less space for us to spend time and resources guessing what you want to do. So if you are calculating sums, means, and so on, always use row sums, call sums, rather than using apply because they are even more specialized and they will be faster. And I have examples of timings for all these things which I can run, or you can run them on your own. So also you can see that how long it takes with the row sum, like about one millisecond. With apply, it takes like 15 milliseconds. That's one thing. Another example again of specialized functions, which min, which max. If you want to know the indices of the minimum and maximum positions in your vectors or whatever you have, it's much better to use a specialized function for this than to use which if x equals min or x equals max, because here again I need to do more calculations more than with a specific function. And then I see that which min takes actually an order of almost an order than the which min specialized function. Also, when you are unlisting things, you should always, if you don't need names, of course, you should always specify use name equals to false, because otherwise R will spend time in time and memory on all these names overhang. So it will copy your names, try to preserve them. It will also try to make them unique, and all that takes time and takes resources. So when you use just unlist, it's considerably slower than if you use it without the names. If you don't need names, use names equals false. And then there are, of course, functions in other packages that do the same thing as the functions implemented in base are, but they do it faster and better just because they are implemented in C++ or whatever, they're just better implemented. So it's a good thing to learn to know about these functions. And so one thing is when you're loading some data, tabulated data, you should use either packages from reader and writers or from data table. They are much faster than the base R read CSV. Also for not most, but for a lot of statistical functions, you have a very fast implementation in RFast package, incredibly faster than faster than the one in the base R. And the final tip is it's R, and it's made it was initially made for statistical computation. So always use algebra, for example, matrix algebra, to solve your problems. If you don't have combined like characters and vectors, if you only have numerics, always use matrices, not data. It will make things much more faster. And if you can rephrase your problem so that you can answer it using just simple mathematical operations, then it will be much faster than looping, much faster than applying. Yeah, and that's basically what I wanted to more or less. For any more details about anything else, I refer you to these 3 awesome books. One of them is Advanced R, that I got most of the material for this workshop from by the man Hadley Wickham. And there are also 2, but there are more of them, books on efficient programming, on R for data science. It's really they are all available. You can read them online. You don't need to buy them or anything. So it's really easy if you have the will to learn how R works and how to use it efficiently. So it's not a bad programming language. It's not a real programming language, but it's not a bad programming language. I will hang around a little bit in case someone has questions, but other than that, that would be more or less it from me.
Thank you very much, Ana Maria. It seems that we don't really have questions in Discord.
Yeah.
So thank you again for a very informative and detailed lecture about how to use R in an intermediate level, and we definitely learned a lot from it.
Thank you. It was a pleasure.
Mm-hmm. Okay, so a little announcement before we end. Next week, we have our main event of this year, the virtual NGS Symposium, which is on Thursday and Friday. We have very interesting keynote speakers, and we have also selected the abstracts. Thank you very much for submitting. So we're very excited for next week, and we invite everyone to join. Please check our website for more details, for example, the program and details about the keynote speakers. So again, thank you everyone for joining. Please remember to give us feedback, and see you all next week.